Supersonic flight hasn't been a challenge for humans for over 50 years. In 1947, Chuck Yeager was the first pilot to break the sound barrier aboard the Bell X-1. At the time, it seemed unheard of. However, just 9 years later, in 1956, they managed to surpass Mach 3, 3 times the speed of sound. So really, supersonic flight has been more than mastered since around the mid-50s. In fact, all modern fighter-bomber aircraft today are capable of supersonic flight. Designing a supersonic passenger plane is a very different thing. This has already been done with 2 models, the Soviet-developed Tupolev 144 and the European-developed Concorde. Both in the 1960s, for several reasons, ended up being cancelled. One of the main reasons was the sound. The sonic boom and afterburner used during takeoff made it impossible for these aircraft to keep operating. However, today we are going to address the problem of the sonic boom, known in Spanish as estampido sónico, and we will look at possible solutions to reduce it. October 14th, 1947. Chuck Yeager on the Bell X-1 was about to break the sound barrier. When all the instruments showed that he was indeed flying faster than the speed of sound, suddenly from the ground. To understand why this happens, you first need to be aware of what sound is. Our ear is made up, among other parts, of a thin membrane that vibrates when there are differences in air pressure. These vibrations are transmitted to our brain, and it represents them to us as sound. For example, this vibrating metal creates pressure waves in the air. The stronger that increase in pressure is, the greater the disturbance in the membrane will be, and the louder the sound you will perceive. An object flying at subsonic speeds pushes air forward to clear its path. But since it moves slower than the speed of sound, the air adapts its shape to the shape of the plane, leaving the perfect space for the plane to pass through. However, when we're talking about a plane flying at supersonic speeds, the plane crashes straight into the air. And now, it's not the air that moves aside to let the plane pass, but the plane itself that hits the air and pushes it out of its path. This impact, the air transmits it to the other particles next to it. And that's literally what a shockwave is, but actually it's much more complicated than that, since a plane won't generate just one shockwave. At the very least, we know there will be 2. For example, with 2 air particles, the closer they are, the higher the pressure. The farther apart, the lower the pressure. Initially, the particles are at rest. The first shockwave compresses them, since this is the impact of the plane against the air. But along the surface of the plane, the pressure decreases, and in the end, there is another shockwave that compresses the particles back to the initial pressure. The N-shaped pressure pattern is always discussed in all the papers. With the sonic boom, a person directly below would feel 2 sudden pressure increases, experiencing a double boom. The gradual pressure drop in the middle of the N goes unnoticed, and this is the key to reducing the sonic boom, making the pressure increases as gradual as possible. In case anyone is wondering, the second shockwave generated by the plane is because, as the plane moves forward, it leaves an empty space behind, and the air has to fill it. So, the first shockwave pushes the air aside, and the second shockwave brings air right behind the plane so that a vacuum isn't left behind. Please don't get me wrong, this is the simplest case. Normally, all objects have more shockwaves, but these 2 will always be there, the one at the beginning and the one at the end. For example, SpaceX's Falcon 9 generates 3 sonic booms, but it's very likely that more shockwaves are generated in the middle of the body, just not strong enough to be perceived. Personally, something that was really hard for me to understand is the fact that a plane breaking the sound barrier sounds exactly like an explosion. How is this possible? In both cases, the same thing happens. Once explained, our video is easy to understand. In a sudden explosion, a certain volume of air expands very quickly as a result of the blast. This rapid movement causes a shock wave to be generated, which propagates through the air. In other words, the sound that humans associate with an explosion is simply a shock wave. That's why any object, including a plane, that generates a shock wave will sound the same. A whip, for example. Of course, the shockwave's intensity will make it sound louder or softer. The sound can range from a small bang to breaking people's eardrums, breaking windows. Or if the energy released is much greater, it could have effects similar to the Beirut explosion in 2020. It is known that on several occasions, supersonic-capable aircraft have been used in war to perform low passes at approximately Mach 1.4 and attempt to harm enemy troops. Many stories exist about this, but nothing is confirmed. But even more incredible is the Soviet project M25, a supersonic aircraft designed to use its sonic boom as a deadly weapon. There is little information available because the project was cancelled and most of it is in Russian. For example, this article says the initial tests were done with the MiG-21, which is its shockwave. It managed to break glass, but it was determined that in order to use the sonic boom as a weapon, an aircraft that was not aerodynamic at all was needed so that its shockwave would be about 5 times more powerful than that of a MiG-21, and with that, they could bring down buildings. They decided to create a special formation to intensify the shockwaves. Depending on the speed at which the aircraft were flying at that moment, they would be closer together or farther apart, with about 5 aircraft in total. We're arranging them so the shockwaves from these 5 aircraft align and their intensity combines. But in the end, the project was eventually cancelled years later. The shockwave's sound caused the Concorde to be banned from flying over land. Many European countries and the United States made this decision as a result of the impact of the sonic boom on the population. Actually, in the United States, for example, to be truthful, it should be said that the Concorde itself wasn't banned, but rather supersonic flight itself was banned. This is where, in 2003, National Aeronautics and Space Administration began to seriously study how to reduce the sonic boom. And the first idea they developed was to optimize the geometry by modifying an F5 known as the Supersonic Sonic Boom Demonstrator. The goal is to generate air compression through several shock waves, in such a way that the sudden jump in pressure would be transformed into several small pressure jumps. This makes the human ear perceive it as several small explosions rather than one large one. When we look at the results obtained with this design, we can see a clear reduction in the pressure jump. So it seemed that this idea worked, and that's why they later continued developing this idea with the Quiet Spike program. A modified F-15 with an extendable nose made up of different cylinders that increase in diameter as they get closer to the body of the aircraft. The idea was to create a series of shock waves before the main one, making the final compression more gradual. The results definitely showed that this method could reduce the sonic boom. That's when National Aeronautics and Space Administration contracted Lockheed Martin to design the X-59, a plane built solely to reduce the sonic boom. It's currently being designed and is expected to fly for the first time in 2022. Supersonic flights over cities are scheduled to observe real-world effects. So far, we've talked about reducing the sonic boom only through geometry, but there are more ideas that surprisingly also seem to work. It's interesting to discover other ways since it's through modified geometry. You would have to spend a lot of resources on the design and manufacturing of the conical parts, which would obviously be very expensive to produce, and on top of that, a lot of space inside the aircraft would be wasted. The first of these ideas is that the nose of the plane should be able to vibrate, expand, and contract. I'm not referring to adapting to flight conditions, as that's similar to the modified F-15 idea, but rather that it expands and contracts at least about 10 times per second. The idea behind this is that the shockwave depends on the angle of the nose, but if this angle is constantly changing, thousands of shockwaves would be generated. What they would do is make it so that to the eyes of a person on the ground, the compression of the air wouldn't be sudden, as if we didn't have a normal plane flying supersonic, but instead it would be much more gradual. This makes sense because a slight change in a plane's shockwave angle at 10-kilometer altitude results in a large ground distance. The effect this would have on perception on the ground is that the pressure spectrum graph would be stretched out a lot and would no longer be abrupt. In other words, that's our goal. The second, entirely different idea involves injecting electrons into the air. The idea is to put a thin rod on the aircraft's nose. This rod at the tip would release electrons that would later be collected on the fuselage of the aircraft. The electrons are released so air particles can absorb them and become negatively charged. And right at the shock wave, in the thin line where the particles are being compressed, there is a high density of them. But if they are negatively charged, a repulsive force would appear, causing the shock wave to go from being a thin line of molecules to a much thicker band, because of these repulsive forces which would force the particles to separate, making the shock wave no longer an abrupt change, but rather a more gradual one. This would change the ground-detected spectrum from its usual N shape to something more like this. Of course, this idea still needs to be developed. There hasn't even been an estimate of how much energy would be needed to put it into practice, nor of how much it would cost. But two things are clear. First, the sonic boom can't be eliminated, but it can be reduced. Maybe to where humans can't even perceive it. The second thing we can be sure of is that the most likely ideas in the near and medium term will focus on geometry and possibly oscillations of this one. The other ideas, like air ionization, plasma use, or similar things, even though they work on paper, are still far from our current technology. But many of you ask me, what is Boom Supersonic going to do to reduce the sonic boom? And even though it sounds illogical, they're not going to do absolutely anything. Their plans don't include reducing sonic booms, as their first aircraft will only fly transoceanic routes. So they don't care about laws on sonic booms. But most likely in the future, once the development of the X-59 is finished, they'll have to start studying how to reduce the sonic boom as well, to try to be able to fly over United States, European, or any other kind of territory. And now, before finishing, I wanted to thank the sponsor of this video for the time I've spent making it. So if you liked it, give it a big like. It doesn't cost you anything at all. And above all, help me share it so that the wonderful world of supersonics becomes more and more known by everyone.